When Hubble was launched, one of its main objectives was to measure the Hubble constant, the expansion rate of the universe.
Charlie? Yes, boys, stand by for a go for release. Minute late. Okay, Charlie.
Flight PDRS.
Go ahead.
The telescope's released.
Okay, thank you.
Beginning in the mid-2000s, around 2005, I started a project to use what are sort of the gold standard tools in astronomy for measuring distances, which is to use pulsating stars called Cepheid variables and exploding stars called Type 1a supernovae, and of course the Hubble Space Telescope itself, and to try to make more precise measurements than had ever been made as a check on the universe. New observations from the early history of the universe, what's called the cosmic microwave background, were beginning to make very precise predictions of how fast the universe ought to be expanding today, and so we wanted to follow up on that by making comparably precise measurements. First, it was the WMAP cosmic microwave background satellite that NASA flew in the early 2000s, and then that gave way to Planck, the European Space Agency satellite, that's even more precise. So by measuring the cosmic microwave background and then using a model that we call the standard model of cosmology to then extrapolate that to the present time, they determined ultimately that the universe ought to be expanding at, in funny units that we use, 67.4 plus or minus 0.5 kilometers per second per megaparsec, which roughly means the universe will double in about 10 billion years. Using the Hubble Space Telescope and some of these tools, the Cepheid variables and the Type 1a supernovae, we determined the local expansion rate to be about 73.0 plus or minus 1.0 kilometer per second per megaparsec, which is the most precise local or present measurement of the expansion rate. But it differs from the expected value, expected that is by the state of the universe shortly after the Big Bang, coupled with our understanding of the universe, this cosmological model. And in fact, those two now sit apart from each other by about 5 times their mutual error bar, which is a phenomenon we call now the Hubble tension. To give you an analogy, it would be like if you had a small child and you measured their height when they were 2 years old. That would be like the cosmic microwave background measurement. And then you used a model of how children grow to predict how tall they ought to end up at adulthood, and that would give you a height. And then you would actually measure when they grew up how tall they were. And so that's the comparison we're making, the present state of the measurement versus what is a very precise measurement in a younger universe, and then a model like the growth curve of a child to predict how tall they will be. Except unlike a child, we've seen many children grow. We have a very good understanding of that growth curve. We've only ever seen one universe, and it's full of stuff whose nature we don't deeply understand. And so it's not crazy to think that we might be missing something in that understanding. In order to predict and really extrapolate the state of the universe from the beginning to the present day, we have to understand components of the universe, particularly 2 components whose nature is not well understood but make up 96% of the universe, and that's dark matter and dark energy. Dark energy makes up about 70%, and dark matter probably makes up about 25 to 27%. And we don't really understand at a detailed level what these are exactly. We don't understand their microphysics. So in order to make these predictions, we assume that they are their most vanilla or plainest possible forms. We see this tension then, and so one possibility, not the only possibility, is that they are more complicated, that there's a more complex story, or some other aspect even that we've been missing about the universe. The Hubble Space Telescope has more or less been working on measuring the Hubble constant for its entire lifetime, about 30 years. So the original goal when it was launched was to measure it to 10% uncertainty, and I think that was successfully accomplished in the early 2000s. We're now on sort of what I would say is the second generation of measurements of the Hubble constant that are targeting closer to percent level precision, and I think Hubble, especially with its new instruments, has absolutely come through with the capabilities needed. Hubble really has delivered the quality and caliber of data that's necessary to make these measurements.